have our next speaker is going to be me. So my name is Jairo Giraldo. I'm a research assistant professor here at the University of Utah. I'm part of the electrical and computer engineering department. I obtained my PhD in electrical engineering in 2015 from the University of the Andes in Colombia. And for the last 7 years, I have been working in cyber-physical system security and privacy. And I joined the University of Utah three years ago. And I have been working in very exciting projects that are very related to cybersecurity and how it relates to resilience in the power grid. So today I will be presenting about the cyber-physical security in power distribution systems. So let's change. Okay, first of all, I would like to thank our contributors. Let me see that this screen doesn't look that well. Second. Okay, this one was kind of cut. Okay, perfect. So first of all, I would like to thank the contributors of this work. Is Professor Masoud Parbania, Mehdi Lanshkani, and Mustafa Gilanifar, which are they were a PhD student and a former postdoc. And the things I'm going to present today are focused on previous work that I have done with them. So cyber-physical power systems consist of all these systems that integrate new monitoring and communication networks in the power distribution system. And the main goal of this is integrating these devices is to increase the state awareness of the system, and that will help to harness the potential benefits of energy storage and distributed energy resources and protection devices, and hence that is going to help to increase the resilience of the grid and to take better decisions of the grid operations. The whole idea of these communication networks is to try to have like fast response, to have an increase on efficiency and modularity, so that new devices and new like DERs can be integrated in the grid. However, as we have heard many times, adding these communication networks, new monitoring, new devices adds also vulnerabilities to a power grid, and it makes it like susceptible to cyber attacks. And there have been several examples of cyber attacks. One of the most known example is what happened in Ukraine in 2015, where there was a blackout that lasted for several hours, and it affected like more than 200,000 people. And it was caused by some attackers that were able to gain access to some elements of the grid, and they were able to cause some cyber attacks that forced the grid to lead to a blackout. Another example, actually not too far from here, happened here in Utah, where some solar and wind assets were affected by a denial of service attack. So some attackers got into the system, and they prevented the communication between the solar and wind assets with the system operator. So there was a time when the system operators didn't know what was happening with their assets. And well, we have other examples that show that actually the power grid is susceptible to cyber attacks, and the big problem is that cyber attackers are becoming more motivated, more resourceful, and for that reason we really need to formulate like new strategies that can assume that maybe the worst type of scenarios that could happen in the power grid. We cannot assume that our systems are already secure. We have to assume that the worst case and try to develop strategies that prevent that make the system more secure, that help us to detect this type of attacks and this type of anomalies, and also that make the system more resilient to these attacks if they are successful. So the main threats and challenges that arise in the power distribution system is that, well, as I mentioned, attackers are usually motivated and very resourceful. And also there are a lot of legacy devices in the grid. So a lot of existing devices that have been operating for a couple of years. They will need to be updated, they will need to be changed, but that's actually very costly. And also patching these devices and software requires like different testing, approval, scheduling, and validation. And that's something that sometimes can be very difficult to do, especially with those devices that are in the field, which are like very hard to constantly change and constantly update. Also, another challenge is that cybersecurity is usually considered after the devices have been deployed, after everything has been installed. People start talking about cybersecurity, and that's one of the limitations that is done after the design and after the implementation. Also, particularly in very low-level field devices, there is a lack of strong regulations in terms of cybersecurity. And something that the previous attacks that I mentioned have shown is that the typical information technology security mechanisms are not necessarily enough. So we can do as much as we can, maybe as a cybersecurity engineer or defender, to prevent certain access to a network, but we have to assume that attackers can be sophisticated enough to actually bypass these typical IT security measures. So that's where physics-based security comes into play. And that's why I'm going to be focused today in this presentation. And what is physics-based security? So one of the things that we know is that attacks on cyber-physical system have a direct impact on the physical process. So if an attacker modifies some control commands in a power grid, is going to have a physical impact, and that's something that we know that is going to happen. Of course, there are attackers that have other different objectives, maybe like stealing certain data, but particularly attacks that want to disrupt the system operation, they have a physical impact that we can observe. And even resourceful and intelligent attackers are bounded by the laws of physics. So we know there are like power flows that we know that if an attacker modifies certain data, with these power flows are not going to be consistent. And we know that there are like very specific ways that the physical system should behave. And as engineers, we typically have a very good knowledge of how the systems behave. So that's something that we can take advantage of. So the main idea of physics-based security is that use our knowledge about the power grid to create strategies that can help to detect, to locate, and to also mitigate the impacts of these attacks. So there are different types of defenses that exist. Of course, the ones that I mentioned, the IT security measures, they are completely necessary. They are the first layer of security that any system should have. There are a lot of best practices in how to handle the security, particularly of the power grid, how to isolate certain types of information to make it harder for attackers to reach to relevant devices. But in particular in cyber physical defense, I want to mention like two main fronts. One is attack detection and localization. So well, the main goal is to be able to identify if an anomaly corresponds to an attack or a fault, or maybe or any other cause, and then determine its location or which device was affected. And this is very important because the response for a fault is completely different to the response for an attack, even if the consequences were the same. So if an attacker caused like a tripping command, caused a tripping of one of the protection relays, maybe the impact is going to be similar if it's a fault or an attack. But the way to solve and to respond to this is completely different. So that's why it's very important to be able to differentiate between faults and attacks. And the other way is to increase the resilience of the power grid. And resilience is the capability to withstand the impact of cyber attacks while it's being clear. So one of the consequences of attack detection, and one of the problems, is that usually we are able to detect this type of very powerful and sophisticated attacks after they have affected the system. So, but we want to guarantee that if an attacker is successful and affect the system, that the system is still resilient and can still keep operating as much as possible while these attacks or faults are clear. So then I'm going to introduce two cybersecurity strategies that we have developed here in the lab. The first one is the fault and attack location and classification, that we call Falcon. The second one is resilient operation of DER constraints. So let me start with the fault attack location and classification. So let's first consider power distribution system. So we know that power distribution system has different monitoring devices and protection devices. We are particularly consider here the fault indicators, which are kind of a novel type of devices that have been installed, particularly here. I know in Salt Lake City they have been installed already. And the objective of these devices is to monitor if there is an actual fault or there's an actual fault in any of the lines. And then we also have the typical protection relays and reclosers that are distributed along the entire power grid. And they are constantly sending information to the outage management system, and they're constantly monitoring the status of the power grid. So Falcon lies in the utility center, and what it does is to take information from the outage management system database after there is an anomaly, and then analyze it to be able first to determine if there is a fault or if it was an attack, and then to try to determine the location of this event, if the location of the device that was affected or the location of the line that was affected by a fault. And what we are and the way that we propose it is using a machine learning based methodology to do this classification and also location. So the methodology, I'm just going to go briefly about the methodology. So the main idea is to collect data from relays and fault indicators, and this data corresponds to voltage and current and the status of the fault indicators. And then we train a multi-class classifier based on deep neural networks using synthetic data from a wide variety of faults and cyber attacks. So we consider like many attacks, many different attacks that cause tripping in the power grid. We also consider different types of faults. We try to create like this very comprehensive database so that we can train Falcon to be able then to take advantage of these unique properties of the power grid. So the data that we use is physical data. So the advantage is that these unique properties of the power distribution system allows the location and classification of these anomalies. And Falcon is able to determine which device is being compromised and the line where the fault occurred. So I'm going to go directly to the case study just to show some examples of this Falcon. So the case study is in the IEEE 13 node test feeder. We consider different types of anomalies. So consider line to ground faults for each line. And we consider like fault data injection attacks and replay attacks that modify the voltage and current of relays, like the measurements that they provide. And also the attack can modify the status of the fault indicators. And one of the things that we consider is that we actually consider the case up to 8 compromised devices simultaneously, which is like maybe the worst case scenario is that all the devices in the system can be compromised simultaneously. And as we can see, the model, we modified the 13 node test feeder, including some energy storage and solar generation, and also including some protection devices that are connected along the entire network. So after doing what I mentioned before, after doing the training in many scenarios and then doing some testing, we're able to find very interesting results. So we divide them in 5 different cases. So the first case is when we are considering that all the data is available, that we have 5 samples of analog variables that have been collected and stored. And in this case, we can and the way that we measure and quantify how good the methodology is we propose these 4 metrics. So we have the false fault location rate, which tells you like the rate or the amount of faults that were not located correctly. Also, we have the false attack location rate, which is the attacks that were not located correctly. And we have the fault misclassification rate, which is the amount of faults that were classified as attacks. And the same, we have the attack misclassified rate, which is the attacks that were classified as faults. Something that we can observe here, and particularly for this case, we are considering up to 3 simultaneous attacks, up to 3 simultaneous attacks. And one of the things that we can observe here is that we have a 50% of error in the false fault location rate, but the other metrics are actually very good. They are very close to zero. So what it tells us is that Falcon is able first to classify correctly if it's a fault of an attack. And the reason is that the signature of the way that the signals evolve when there is a fault, they're very different and very distinctive when there is an attack. And it will actually require an attacker with extremely sophistication to be able to replicate exactly what is going on in the entire grid. But the reason of this 50% is actually because we observe, and it's usually between adjacent lines. So locating the fault in a particular line or the one that is next to it can be a little bit more difficult because the signatures or the way that the waves behave are a little bit similar, but still 50%, we can say that it is still a very good result, especially because we are considering like up to 3 cyber attacks simultaneously. But the things that we wanted to actually explore also is what is the effect of these other inputs that we have in the system. So particularly something that was very interesting is what happens if we don't have those fault indicators in the system, which and something that we can see here is that that false fault location rate increases significantly when we remove the fault indicators. And what it tells us is that fault indicators actually provide very important and very relevant information to be able to locate these faults accurately. And still, these fault indicators, they don't have that much impact in the cybersecurity aspect, but to be able to differentiate and find the location of the fault, they play a very important role. The third case is when we don't consider the data of the protection relay. So we are assuming that each DER has some protection relays associated close to them, and if we don't consider the data of them, then now we are going to observe some errors in terms of the attack misclassification rate. So some attacks now are going to be misclassified as false. So that means that this collecting information from the DERs also provide like very important information to be able to classify like faults and attacks. The other case is that what happens if we ignore the voltage information. So sometimes in protection we focus a lot in current, but what happens if we don't consider the voltage information? We can see here there is a significant increase in the false fault location rate, and also we have an increase in the false attack location rate. So that means that voltage actually helps a lot in terms of finding these particular locations of the faults. And finally, the other case that we want to consider is that instead of having 5 samples of data, we are going to consider only 2 samples of analog variables. And we can see that still the system has a relatively good performance. Still, of course, there is going to be an increase in the false fault location rate. Then the other case study that we wanted to explore is what happens when we start considering like different numbers of cyber attacks simultaneously. So what is going to happen is that if we consider like multiple cyber attacks simultaneously, then it's going to increase actually the complexity of the entire classifier, and that is going to affect the accuracy of the system. So that means that if we want to consider like the worst case scenario, which is up to all the devices can be compromised, we are going to have some accuracy issues that are affected because the complexity of the system also increases. But still, considering like 3 attacks simultaneously provides a very good performance. So what I mentioned previously was focused on Falcon, which is fault and attack location and classification. But now I want to focus in the other part that I mentioned before, which is the resilient operation. So as I mentioned, one of the important aspects is that we want to guarantee that even if an attack is successful, the system can still continue operating. So the motivation is that cyber attacks can actually bypass security mechanisms, and attacks as I mentioned before, can be detected usually after they affect the power grid. And typical existing security measures cannot guarantee that the system will remain safe even if the attack is successful. So what we propose is a novel mechanism that guarantees that any cyber attack cannot drive the power grid to unsafe operation state. So I'm going to focus in this example in the frequency control of the power system. The frequency control of the power system, but the methodology that I'm going to introduce is going to be is applicable to many other strategies. So here we can see that we have an attacker that can affect the control signals and can affect the sensor measurements. And what we propose is to add these resilient constraints, which are like new additional constraints that are going to limit what an attacker can do to the system. And the way that we do it is that we define what is called the attacker's reachable set. And the objective is that we want to try to compute that reachable set and make it and shrink that reachable set of the attacker so that the attacker can never reach unsafe operation states. And this will guarantee security against any type of attack that affects the control commands directly or that affect the sensors. So this methodology is usually done based on linear time invariant systems, and the objective is to find the largest constraints that can guarantee that this reachable set doesn't overlap with unsafe states. I'm just going to go through some examples really quickly. So this is an example. What happens when we don't have these resilient constraints? So in this case, we assume that an attacker starts here after 0.5 minutes. And this is a random attack. We see that an attacker that falsified the AGC control commands randomly can actually reach the system states to reach unsafe operation. And if we consider some optimal attack sequences, we can also see that an attack in the AGC can drive the system to unsafe operation states. And this is just an approximation of the reachable set, and we see that there is an overlap with the unsafe states. But when we include these resilient constraints, we can see that the attack is now bounded, like the consequence, the impact of the attack in the frequency regulation is bounded, and there does not exist actually any attack sequence that can drive the system operation to unsafe states. And this is just how the reachable set looks like, and it doesn't overlap with unsafe states now. So in conclusion, these unique physical properties of the power distribution system enables the development of a variety of defense strategies. And we know that Falcon is able to classify the type of anomaly and determine its location with high accuracy. And the resilient operation constraints are able to limit the impact of very powerful attacks. And these strategies provide different layers of security and resilience. And thank you so much for your time. And I'm glad to receive maybe one question. I think we have time probably for one question. Any question from the audience?
Thank you very much for the presentation. So in the finding the reachable set safe region for that that you described in the last part of your presentation. So how do you guarantee that the attacker stays in the safe region? Do you control of that?
Yeah, that's a very good point. So the whole idea is that these resilient constraints actually lie next to the devices, so next to the DERs. So even if an attacker injects, let's say, like a set point that is 1 million of something, then these resilient constraints are going to limit that, and they are going to block that. So yeah, the whole idea is that these resilient constraints will lie next to the actuator. So any attack signal, depending on what it is going to be bounded.
Thank you very much.